October the 19th, a Thursday. Yesterday evening I had a lovely tennis match. We all played well, so it was very much a mental game. And that's quite clear as we shifted being on top. First, the other team, it was double, the other pair, came ahead 2-0. Then we won 6 games in a row to win, I think it was 6-3. So we were on top there, really were. And then in set 2, we lost 4 games in a row, and then we won 3 in a row. So it was simply a question of what was going on in our minds. Now, before starting on problem 7, I'll just show you something I did in relation to problem 6. And that's the modular forms of weight 4 and 8, not 12, but 16 and 20, and not 24, have a 0 at omega, which has this Q value. And mimicking what we did in problem 6, we then get this sum, and that should have this result. So I tried computing it, and it turned out to be true. And then we have shifted the value of k once, of course, as we did in problem 6. So in 3 it agrees, and 7 agrees. 11 it actually changes sign and seems to be close to minus 2 times this result. 15 agrees. 19 agrees. 24, it's the same. 27 agrees, and 30. Now this sum, I might have experienced it as a function I wanted to compute as a function of x. I don't think a mathematician in 1,000 lifetimes could expect to want to know the value of that sum at this particular point. But, well, who knows? Now we have the result. And this, of course, this disagreement means, of course, that E12 does not have a 0 at omega. If it did, it would be a 0 of order 3, because 12k divided by 12 gives unity. So if we have a 0 at omega, which in the sum, I've forgotten the name of the proposition, well, never mind, would have to be a triple 0. And that means that E12 divided by E4 cubed would be a modular function, no, a modular form, as the 0 would cancel, and it would even tend to unity as q goes to, or z goes to infinity, I infinity. So it would be a modular form, and none exists, so that can't be. So this disagreement was fully expected. All right, I just wanted to show you this before heading on to f is a modular form of weight k. And we assume k is even, so we don't care to write minus z to the kth. And then it has no poles, not even at infinity. And then we shall prove the same almost for G. Differentiating this gives the same, and it holds for E2 as well, and it did for F, so it's G of Z. That was the easy one. So what we do here is that we substitute Z with minus 1 divided by Z. And first we need to differentiate F. And we differentiate with respect to Z. Oh, that's where the 2 comes from. So we just multiply with Z squared. Oh, that gives ZK plus 1. Next, we must use the transformation formula for E2. And I actually looked up the page where we have it. It's Z squared E2 of Z plus 12 this is what we need here. It's just copying it. Now where did that... Oh yeah, that's 12 Z squared divided by 2 pi I Z. And then Z to kth F of Z. And we reduce these two guys cancel. Meaning we are left with now what was this? That was actually the number 12. And we see that this is actually G of X, 1 divided by 2 pi F, the derivative of F, minus K12, the E2 times F. So this gives X, Now z, why do I keep writing, this is z as well, z to k plus 2, or do you say raised to k plus 2 times g of z and of course it's an algebraic expression, polynomial expressions, so it's a form, it has no poles. That was the first part. Now assume that f of z tends to naught as z goes to I infinity. Let's actually do the expression plus higher terms. And taking the derivative so this is the guy. So you see it has no constant term, it tends to naught as well when z goes to I infinity. So that means that they all tend to naught, meaning it's also a cusp form. That was a nice result, and surprising that we can get the derivative into the question with the help of E2. Right.